For a reaction to proceed and for a reaction to be practical to us, two things must happen. The first one is that the equilibrium favors the formation of the products, and the second one is that the reaction happens in a reasonable amount of time. In other words, it happens fast enough for us to be worth it. These two conditions depend on two different concepts that you had seen before in general chemistry. The first one is thermodynamics, and thermodynamics tell us about the energies of the reactants and the products. And what it also tells us about is how much of the reactants you have at any point and how much of the products you have at equilibrium. Not at any point, but at equilibrium. That's what K equilibrium tells us. And then the kinetics, what it tells us is how quickly that reaction happens. So again, there's a big difference. First one, thermodynamics tell us about the energies of my reactants and the energies of my products and how they compare. And kinetics tell us how fast that reaction happens. So at the equilibrium constant, remember it has these expressions where we have the concentrations of the products here on top divided by the concentrations of starting material. So in a reaction such as this one, A plus B gives us C plus D, we will have the products right here that are C and D. Those are the concentrations. And here we have them divided by the concentrations of A and B. So the size of Ka, so the number here of K equilibrium tell us if we have more of the products or more of the starting materials. So when this number is larger than 1, so when the K equilibrium is larger than 1, then we know that the equilibrium favors the products. The reason being is because we have more of the top, we have more of C and D, so that's why the K ends up being a number that is larger than 1. But when the K is smaller than 1, then it means that the reaction is favoring the formation of starting materials, which means that the equilibrium goes to the left as this reaction is written, right? So what it's interesting to us and what it's practical is we want to have a K equilibrium that is larger than 1. So this is similar to what we saw in acid-base reactions. We would look at if the reaction was moving forward or if the reaction was moving backwards, and we always were interested in reactions that were moving forward. So the same here. We want to have reactions that have a K equilibrium larger than 1. So again, for us to, we want reactions that have that K equilibrium larger than 1, and so the reaction is moving forward. So how do we decide if the reaction is going forward or backwards? Well, to do that, we look at the delta G. To do that, we look at the equilibrium constant and the free energy. So what we want to have, again, is a reaction that is moving forward. And our reaction will move forward when the delta G, and remember this is the Gibbs free energy, right? The G right there. So that we want the reaction to move forward, and that only happens when that reaction has a negative sign for the delta G. So let's look at two examples here. When the delta G is positive, then that means that the K equilibrium is smaller than 1. And so then the reaction will proceed backwards, because the energy of the products will be larger than the energy of the reactants. So the equilibrium goes back. On the other side, when the delta G is smaller than 1, then that means that the reaction, the K equilibrium will be larger than 1, and that will favor the products. So we are interested in reactions that have a delta G that it's negative, and reactions that have an K equilibrium that it's larger than 1. So this is what we want right there. So the relationship between the delta G and the K equilibrium is given by this formula. So here we have a constant, we have the temperature, and we have the log of K equilibrium. So again, when we want the K equilibrium to be larger than 1, so that gives us a positive logarithm of K equilibrium, making the delta G negative, right? So look at this relationship. We want this number to be positive and large, so this could be negative, because look at this sign that we have right there. We have a negative sign. So in that way, when the delta G is negative and the K equilibrium is positive, or it's larger than 1, then we can the reaction can proceed. So on the opposite, when the K equilibrium is smaller than 1, then this logarithm of K equilibrium becomes negative. And so because we have a negative sign multiplied by a negative sign, then this becomes positive, and then the delta G becomes positive, and the reaction does not proceed towards the products. It goes backwards. So we want to have a K equilibrium that is larger than 1. In that way, we have a log that it ends up positive, giving us a negative sign right here in the delta Gibbs. So like we saw here, right? We want to have these to be positive. So when we multiply by this negative sign, we end up with a negative sign. And so if we look at the relationship of these two, we see that a little change in the delta G, look at these numbers right here, becomes a huge change in the K equilibrium. So something as small as 6 units of difference in the delta G corresponds to 100 times, 10 times larger the amount of one of the reagents versus the other one, right? So here we have this reaction. A gives us B. So 6 numbers or 6 units of difference results in 10 times as much B than as A. So let's look at one example. In this example, we're looking at the delta G of these two conformations, right? So here we have a conformation where the phenyl ring is in an axial position, and here we have a conformation where the phenyl ring is in an equatorial position. Based on what you know, because we've seen conformations before, you know that this equatorial is much more favored because the larger groups prefer to be in the equatorial position. So that's why the reaction will favor that. But how do we demonstrate it? So what we do is that we simply plot that delta G that it's given to us in this equation. So we know that if we use we plot it right here, we can end up with the K equilibrium if we use the R, if we put the temperature, we end up with a K equilibrium that is 100. So that is telling us that there is 100 times more B than A at equilibrium, right? So when the delta G difference is about 12 kilojoules per mole, what we end up getting is that the K equilibrium is 100, and so that tells us that there is 100 times more B than A. B is favored. So let's go back to that table. So you see here we have a minus 12 delta G that tells us that the K equilibrium is going to be about 100 times, and so we're going to have 100 times B as more B than A. So here's exactly what we saw. When we have a minus 12 difference and we plot it in and we use the constants, we end up with that K equilibrium being 100. You don't have to memorize these numbers. I will never ask you for those, but you have to understand what they mean. So what you have to understand is that when you have a K equilibrium of 100, that means that you have 100 more times of this conformation than you have of this one right here. But remember, you don't have to memorize these numbers here. You just have to understand what they mean. So we talked about an enthalpy, we talk about delta G, and now we're gonna talk about entropy. Entropy tells us about the degree of disorganization of a system. So it's often we often talk about the entropy, as a measurement of the randomness of the system. So you can also think about it as disorder, right? So that's a word that we're going to use, disorder. So the system will always tend to be disorganized, right? So then if a molecule is in a solid state, it will be more organized, right? So if it's in the solid, it will be more organized than if it's in the liquid, and that if it's in the gas. In the gas is in the most disorganized, so the entropy will be the largest. Then we also can talk about cyclic molecules. So when a molecule is in an open chain, it's more disorganized, but when the molecule cyclizes, it has less movement, and so then the entropy diminishes, right? So here the entropy goes down because we are going from an open chain and all these bonds can rotate, right? They are all single bonds, so they can all rotate. But here you limit that movement by locking it into a close, into a cycle. So again, the entropy tells us about the randomness of the system. So when we go from one single product, just like here, we have one single reagent, and we end up with two reagents, what happens is that the entropy increases in this situation, because here you had them both locked in one position, and here you increase the randomness or the disorganization. And here is what we were talking about before. So here I have an open chain, but when you lock it into a cycle, then the entropy diminishes, right? So this is more disorganized than this is. And so how do all these terms relate? We have the total energy change in the delta G, then we have the enthalpy, we have the entropy. So you've seen this expression before, and so this total energy is due to both the enthalpy and the entropy. However, this term, the entropy change, is often smaller, so we often associate delta G with enthalpy, right? So unless this term is really, really big for some reason, most of the total energy of the reaction will come from here, from the enthalpy. And so that's why we can disregard this term. And so we've seen some of the reactions where the entropy actually plays a role. So one is when you have one single molecule and you end up with two because the entropy increases in this case, or the other case is when you have an open chain molecule and it cyclizes, and then at that point the entropy decreases. So again, here you have a summary of all these terms, of what each one of these terms means. So we have the entropy, that refers to the freedom of movement of the reaction, to the disorganization of the reaction. The enthalpy is the amount of energy that it's released in the form of heat when these reactions form or when they break. So remember that if a reaction is endothermic, you have to put energy, and when the reaction is exothermic, the energy will be released. And this is how these two terms relate via giving us the Gibbs free energy.